Premier orateur de l'après-midi est Stefan KEBEKUS, qui parle des travaux récents de Cartier Birkar sur les variétés de Fano.
Thank you so much for the introduction. Also, thank you for the invitation. Great pleasure to speak here. I'm supposed to speak about the work of Birkar on boundedness of Fanos and applications. But before getting there, let me spend maybe 15 minutes explaining what the objects are and how they fit into the larger world of algebraic geometry. So I start with Fano varieties. So what is Fano? A manifold, a projective manifold, is called Fano essentially if it's strictly positively curved. I need to make this precise, and the correct definition is a projective manifold. By the way, everything I'm going to say is over the complex numbers, is called Fano if the canonical line bundle or, if you wish, you take the cotangent bundle and then the determinant, explain their importance and how they show up. For curves, this is very well understood. So let me recall. If x is an algebraic curve, or if you wish, Riemann surface, compact Riemann surface, there's basically three possibilities. So then either x is P1, and this is Fano, or x is an elliptic curve, and this may be, I could call Calabi-Yau, or x is of general type. So we have this trichotomy for curves. Something is either positively curved, flat, or negatively curved, parabolic, flat, hyperbolic. There's many adjectives that I can choose that make these three classes distinct. And ideally, we would like to have something similar also for varieties of higher dimensions. But of course, already for surfaces, things are complicated because obviously I can take P1, which is positively curved, I take another curve that's negatively curved, take the product, right? So this is something that could happen for surfaces or will happen. So let me list two of the major difficulties. So what about surfaces? And I have problems, namely I have products, or more generally vibrations. And then there's something, another problem is namely that I have blow-up. What is blow-up? Blow-up is a form of surgery that we have in algebraic geometry where you start with a surface, say, you choose a point, and then the surgery allows you to find a new surface, x twiddle, where the point gets replaced by a curve. And the canonical class will, on that curve, always be negative. So if you start with a surface where the canonical class is the most positive, and you say, we're in like one pure case, you can always add some negativity to it by blowing up. So we can blow up. So that is surgery that replaces a point by a curve on which omega x is negative. Now, what do we do with these problems? Of course, for problem number 1, there is no escape, right? This is something that can't be avoided. I have products. For problem number 2, there's an almost obvious solution, is that maybe we shouldn't be looking at all surfaces, really. We should be looking at minimal surfaces only, that is, surfaces that are not blow-ups of others. So now I have to figure out so solution at least to the second problem is look at minimal surface only. And minimal is surfaces that are not blow up of others. And once you're willing to do this, then we have a trichotomy that is somewhat similar to the ideal case that we have seen for curves. So let me state this as a fact. And this is classical algebraic geometry of the late 19th and early 20th century. So if x is any projective surface, then x is a repeated blow-up of a minimal surface y, and, well, y is either a projective space again, so that is positively curved, or it's a P1 bundle, which, well, is something that we definitely expect to see in product situations. So let me call this a Fano bundle, viewing P2 as a trivial bundle over a point. So this is maybe a Fano fibration. Or Y is a torus abelian variety, or there's 2 other classes of classically known surfaces. These are K3 and Henri's. K3 Henri's surface. So these are classically have classically been studied, or it's an elliptic fibration. So elliptic fibration. So, and let me call this Calabi-Yau fibration. So Calabi-Yau carries no meaning here. This is just a shorthand for this things that we have here. Or Y is of general type, and omega y is positive. So this is a classical fact that I would like to see as some form of unmixedness or decomposition theorem. You start with any surface, you blow down, you revert the blowing up process until at the very end you end up with a minimal surface, and that minimal surface will always have the structure Fano fibration, Calabi-Yau fibration, or it's of general type, and then it's positive. So this is the best form of decomposition that we can hope for, accepting the fact that we have to deal with products. So this is, again, very classic and well understood. Now, what about higher dimensional varieties, which is the subject that I'm discussing today? And there is not yet a fact. There is a conjecture that things work pretty much the same. Everything is more complicated, hugely more technically, and technically involved. And not everything is proven, but a lot has been shown. So let me ask, what about higher dimensions? And the answer is a conjecture, which has been proven in large parts also due to the work of Birkar, which basically says the following. So if X is a projective manifold of any dimension, then there exists a sequence of birational transformations that are similar to blowing down, and I'm not going to make this precise. So then there exists a sequence of birational transformations somehow higher dimensional analogs of blowing down, starting with X, and then after finitely many steps going to Y, where Y is a variety of the following form. Namely, A, Y is a fiber space, and the typical fiber is a Fano variety. So Y is a fibration, typical fiber is Fano, or Y is a fibration, typical fiber is Calabi-Yau, or Y of general type, and omega Y is, again, positive. So this is essentially what I would like to convey in the first quarter of my talk. Fano varieties are very important because they appear as fundamental building blocks in birational geometry. And if this conjecture were true, which most of us believe, then any variety is built out of Fanos or built out of Calabi-Yaus. You start with a variety. There's a set of well-understood birational transformations similar to blowing down. You end up with a minimal one. And the minimal one is either negatively curved, or it's a fiber space, and the fibers are either Fano or Calabi-Yau. So Fanos are important. There's, however, a catch. Namely, things do get technically complicated in higher dimensions, and it is well understood that whatever your higher dimensional analog of blowing down is, if you want a result like this, you got to deal with singularities. There's no avoiding this. So I have written here variety because I can't say manifold. So the catch is there's a price to be paid if you want to have something like this already in dimension 3 where everything is understood. Then you got to deal with the singularities. Is there? Here. Thank you. So problem. Y, and also the general fibers, or the typical fibers, cannot be expected to be smooth. Instead, they exhibit a class of singularities which is very mild, known as terminal singularities. Note that the usage of the adjective terminal is precisely opposite to what you have in medical school. Watch out, Y and typical fibers will generally not be smooth. They will have terminal singularities. And since all of Birkar's work has to do with these classes of singularities, actually this is the whole point. I should take 2 or 3 minutes and explain what they are. So what is a terminal singularity? Definition, a variety W, we say, is terminal if the following holds, namely A, it is normal. So the singularity set already is of codimension 2, which is a good thing, right? Then secondly, the definition of Fano already involved this line bundle of holomorphic top forms. Now I'm on a singular space, and I would have to vary what holomorphic top form actually means. This is maybe not so obvious, but part of the definition is that for terminal spaces, this problem goes away. Namely, what do? I look at the bundle of holomorphic top forms, but only on the smooth locus. And I claim that if I take this bundle to a certain power, so there exists a power such that this extends to a line bundle on all of that space. And then this is W now. All right, thank you. This is W. Right. So that saves me from trying to define what differential forms are in a singular space, right? I just work with this line bundle, and probably I should give it a name. A line bundle, say, L. And then C, so the pullback of differential forms extends to a map. So from pi upper star L to omega. So for any resolution of singularities pi from x twiddle to x. So whenever I have a morphism of spaces, I can pull back differential forms. There's a twiddle missing. Oh, W again, sorry. This might become the running joke of this talk. I should stop using W's. Right, so whenever I have a morphism of spaces, I can pull back differential forms, and then when I can pull back differential forms, I can also take like pluriforms. And this condition tells me that pullback just works with this line bundle here. And better still, so pullback forms have zeros. Pullback forms have zeros. So they, whenever I have, say, a singular space, I resolve the singularity. That will replace a singular set by a divisor. Then these pluriforms that come out as pullbacks, they have zeros along E, like you would expect for any regular, any morphism between regular spaces. So in a nutshell, this says the terminal singularities really are not so bad. They're normal. This could be seen as saying that, well, the bundle of top forms maybe is not actually a bundle, but more like a Q bundle. And this ability to pull back forms essentially says that things that you would prove on a manifold with differential forms in L2 theory can be proven on that singular space as well. So typical examples are vanishing theorems, cohomological vanishing theorems that come out of L2 theory. On spaces where that singularities, they generally work. Everything gets technical, of course, but this is basically the idea. So, and coming out of this is then essentially the understanding that, oh, I should say Fano. So W is Fano if L is anti-ample. That Fano varieties are very important. They appear quite naturally. All varieties are somehow composed out of varieties of general types, Fano fibrations and Calabi-Yau fibrations. So as a minimum, we should understand like how many Fano varieties are there to start with, and then how can they possibly fit together to form bundles. And Kosha has answered the first question. So let me then try to formulate Birkar's result, which was explicitly mentioned in the quotation for his Fields model. That is given D, then D-dimensional terminal Fanos form a bounded family. What is a bounded family? A bounded family means that there is a projective morphism between schemes of finite type, in particular finitely many connected components, such that every d-dimensional Fano variety appears as a fiber. And instead of writing this down, let me just write down a few consequences of boundedness, which might be the most relevant for us today. So consequences are there's only finitely many deformation types. Only finitely many deformation types, or there exists one big projective space such that every d-dimensional Fano variety lives in there. So all such varieties can be embedded into one Pn, where n is very large, and described there by equations of bounded degrees, but okay, we are not going to write this down. So this is his result. A few remarks probably in order. For manifolds, this has been known before. So remarks. So the manifold case is due to Kolla, Miyaoka, and Mori, with important contributions by Campana and also Nadel. Also, Birkar's result is, of course, much more general. Result is much more general. In particular, it applies to a much larger class of singularities. However, let me show a silly little example to illustrate that some assumptions on the singularities is actually required. So maybe an example or a non-example, I don't know. So I let the nth roots of unity act on P2 via the simplest action I can imagine, multiplication in the first two coordinates. So set xn is Pn P2 modulo this action. Then these are quotient surfaces, so they have quotient singularities, and you might ask, like, how bad can this be? Quotient singularities is not so. So whether the canonical bundle here is a Q bundle or not, that question is all trivial. Come on, it's a quotient. And a curvature of this is also, I mean, if anything deserves to be Fano, it's this, right? However, these surfaces do not form a bounded family. These surfaces do not form a bounded family because if I had only finitely many deformations type, then all the like invariants that I have of singularities that vary semi-continuously in families take only finitely many values. But here these quotient singularities, the index of the quotient singularity is exactly n. So this is not a bounded family. And the singularities are really not so bad. And to illustrate what Koshaw's result really is, let me just draw a stupid. So in birational geometry, there's a measure for how bad singularities are. It's the discrepancy. I'm not going into any details. So here's the discrepancy. And this here means bad. So we have terminal singularities that are not so bad. The next class in birational geometry is called canonical, and then there's log canonical. And this is generally at the boundary where things in birational geometry work. So if you're in this side, there's stuff you can prove. Here's stuff you can formulate and maybe prove or maybe not. And on to the right, often you can't even formulate. So we have these surfaces. We have x1, x2 already is canonical, and then the others, they converge against log canonical. And what Birkar's result really is, you need to choose an epsilon, and then stay an epsilon away from log canonical, and then you have boundedness. So that is his result. And it answers the first question, like, what set is this set of Fano varieties really? So this has major applications. One set of equations that applications that I'm not going to discuss today is existence of special metrics and K-stability. So instead, I would like to discuss one application to the structure of the Cremona group. I should point out that earlier this week, a preprint appeared by Jérémy Blanc, Susanna Zimmermann, and Stefan Lamy, where they give another very substantial application of Birkar's result to the Cremona group. Susanna has given a talk here in Paris last Monday, I think, or Monday this week. So let me not repeat this. Also, I haven't had enough time to prepare. Instead, let me turn to the Cremona group and its Jordan property. So this is application to Cremona group. Now, what is the Cremona group? Recall Cremona group. This is the C automorphisms of the field of rational functions in n+1 variables, or, if you wish, it's the group of birational transformation of Pn. And for today, I would like to take the second point of view. I would like to view the Cremona group as a group of birational transformation because this is more geometrical and will allow me to argue by geometric arguments. So then there's the word Jordan property of the Cremona group. So what is a Jordan property? Generally speaking, the Cremona group is a very large group that has been at the center of interest for probably over 100 years and is still understood only in part. Its structure remains mysterious in large parts. However, there is the general feeling that when it comes to finite subgroups, the Cremona group and linear groups are not so different somehow. How is maybe not so clear, but the Jordan property is one example. And let me recall the classical result of Jordan, 1877. I believe it might have been his thesis, but maybe people here will know better. So given a number D, there exists J such that for any finite G in GLD C contains an abelian A of index G over A is no more than this Jordan constant. And it has been, Serre asks if something similar holds for the Cremona group. And the answer is now yes. Even more generally for a large class of birational transformation groups. So the theorem, which is much older than Birkar's work. It's an observation or a result of Prokhorov and Shramov. They realized that if somebody solves boundedness, then that would have the implication that a Jordan constant would also exist for many birational transformation groups. So the theorem is Prokhorov-Shramov given D, there exists J such that for any d-dimensional rationally connected variety X, comma, any finite group G inside is group of birational transformation contains an abelian such that, and so on. So same thing, but for rationally connected varieties and all of them together. So there exists one Jordan constant that works for all those varieties and their birational transformation groups. However, I should say what rationally connected is. Rationally connected is like projective space. In projective space, if I'm given any 2 points, they're connected by a line. And a line is a rational curve. A space is rationally connected if any given 2 points are connected by a rational curve, which might be a line or might be of higher degree. So def rationally connected is any two points joined by a rational curve. And important facts to remember is Fanos are rationally connected. This is, comes out of Morris' work, and I will say a word about this near the end of the talk. And also there's the classical Lyrod theorem that tells us that the image of a rational curve under any map is either a point or again a rational curve. So that implies pretty immediately that images of rationally connected are rationally connected. So. Now, irreducible, absolutely irreducible. This is critical. Yeah, maybe I should by irreducible. Right. So how do you prove this result? Sketch of proof. That maybe also illustrates a little the techniques that come later when I say a word about what Birkar actually does. So the first step is let's forget about birational and look at automorphisms. Look at automorphisms, and step 0 is the observation that fixed points help. Namely, if G in the automorphism group of X, now honest automorphisms is finite if X in X is G fixed, then Gx on the tangent space, or on the Zariski tangent space if the fixed point is a singular point. And that action here is not just any action, it's actually faithful. The effect that it's faithful is a classical linearization at fixed points. There's results about this, but here in the situation where we have finite groups of automorphisms, this can be done by just looking at the Taylor series expansion of the group action, and this was certainly known to Cartier and also Minkowski. This is a very old observation. So that means that our group really is a linear group, and the classical result of Jordan applies. So nothing to be done in that case. So Jordan says done. So what we should be looking for if we want to prove this result on the Cremona group is we should find fixed points. And this is where Birkar's result comes in. Birkar's result in this business is a means to find fixed point. And here's how it goes. So this is step 1. That basically says given a number D, there exists a Jordan type constant F, and for any d-dimensional terminal Fano, and any d-dimensional terminal Fano and any G in the automorphism group, a subgroup F in G such that F has a fixed point, and the index is bounded. So I find fixed points after passing to subgroups of bounded index. So for all practical purposes, this is as good as saying that G has a fixed point. And how to do this is, so Birkar has told us that all these Fanos, they can be embedded in one projective space. And actually, that embedding, I haven't told you that embedding can always be chosen to be equivariant with respect to the action of the automorphism group. For the experts will realize that the canonical bundle always carries a canonical G linearization. So the idea, so embed using Birkar's results all x out equivariantly into 1Pn. So then the group G that we have lives in PGL n. This is covered by GLN. We look at the pre-image. This is now a group morphism of bounded index. Bound is n, essentially. And the classical Jourdain result says that gamma is as good as abelian. So gamma as good as abelian. Okay, you could say, but now we're done. But really what I have in mind is this is abelian. And then the classical results, it might be an overkill, but there's the Borel fixed point theorem. But for these finite groups, probably the result is much older. These groups have fixed points. So gamma is the same as, well, no. This has an abelian, and F will be the image of the abelian inside G. But for now, I just say, but abelians have fixed points. So I find a fixed point after passing to subgroups of bounded index. So this is how I would like to find fixed points for Fanos, but this is not yet quite what we need. So step 2 is same for rationally connected varieties. So I would like to extend that result replacing Fano by rationally connected. Now how do I do this? And I will just draw a little diagram and explain this in words. How do I do this? So we start with a variety that's rationally connected, nastily singular maybe. And we have the group G, finite group of automorphisms acting on there. Then I can resolve the singularities. Resolving singularities, there are many ways to do this, but Hironaka has given us one preferred resolution of singularities, the canonical resolution of singularities, and that will always be G equivariant. So very good. I can already assume that my space is smooth, right? So then I apply the minimal model program, this sequence of birational transformation that are like blowing down. I come to my space Y, and my space Y is a fibration, and in this setting with rationally connected and many rational curves on there, it can't be Calabi-Yau, too many rational curves. So this will be Fano fibration. Now, I like to find a fixed point. Okay, I can find a fixed point here. The blowing up morphism, the resolution morphism is equivariant. Then I have the minimal model program here, and this can also be set up in an equivariant way. Prokhorov and Shramov do this, and by understanding the individual steps of the minimal model program in all detail, they realize that, okay, not only I have a G action here, but it suffices to find fixed points here. Because they understand the steps of the minimal model program in detail. Aha, but now we have a fiber space. Oh, this is also G equivariant. This is part of the minimal model program. Very good. This will have lower dimensions, so I can apply induction. So I get a fixed point here, which means I have a stable fiber. The fibers of the Fano fibration, however, are Fano. Well, most of them are. If the fiber is Fano, I can also apply step 1. And if the fiber is not Fano, then, okay, things get technical. It's a limit of Fanos, still rationally connected, still induction works, but everything gets so much more technical. So this is, now I should write down something. Prokhorov and Shramov say, use the minimal model program to argue by induction. The minimal model program brings you to a fiber space, and that fiber space structure allows you to argue by induction. And this is something that, by the way, Birkar also does all the time. And now we're essentially done, except that the result pertains to actions of the birational transformation group and not the automorphisms. But then, so step 3, if X is rationally connected and G in the space of birational transformation groups is finite, then a classical result of Sumihiro says I find a birational model where G acts by automorphisms. Honest automorphisms and not just by rational maps. Yeah, basically you blow up the indeterminacy locus of your finitely many birational transformations. And now we're in business because we have an honest action by automorphism group. So step 2. Step 2 guarantees we will have fixed points, and then step 0 says, okay, once you have fixed points, your group is as good as linear, and the Jordan property applies. And let me not even write this down, and instead finish there. So this is how you can apply Birkar's result, and now I have about 10 minutes to tell you how Birkar's result is actually shown, and this is of course impossible. So instead of going to Birkar's result directly, let me at least say a word how it's been done for manifolds in the 90s, and then I will just point to what more needs to be done in the singular setting. So this is how to prove boundedness. For manifolds. The proof of boundedness for manifolds involves like 3 or 4 major ingredients, and let me just list them. First is the fundamental work of Mori. Mori has essentially shown to us in the early 90s that once you have some positivity in the curvature of your space, you will find rational curves. And this result has been, that was his Fields Medal work. This result has been generalized by many people, including Kolamiya Okamori himself. Mori, and again, I should definitely mention Campana here. So if D if X is the dimensional smooth Fano, then X is covered by rational curves C such that the first Schoen class of the tangent bundle times C is less than D plus 1, I hope. Olivier probably knows better. Is this D plus 1? It's D times D plus 1. So I have my space X. And on that space X, I find many, many, many rational curves whose intersection number is bounded like so. So this is first main ingredient. The second main ingredient is a very classical result that probably goes back to Giuseppe Fano, and nowadays we would call it the asymptotic Riemann-Roch. Fano, Riemann-Roch. He basically says that if the top intersection of, I should write the first Schoen class of the tangent bundle. If the top intersection is large, then I find a number n and a hyperplane, say D inside minus mkx with a point of high multiplicity. So this is now becoming a little technical, but let me just draw what's going on here. So here's our space X. Assume this is large, then I find a surface with a point of very high multiplicity. And this surface will be cohomologous to a certain power of the first Schoen class of my space. On the other hand, Kolla, Mia, Okamori, they give me lots of rational curves whose intersection number with the first Schoen class is not so big. So these two things play off one against the other. This says here it needs to be big because when I have a very singular surface and the curve passes through the singularity, then the intersection number is at least the multiplicity. Here it says, but it can't be so large. So together, this gives that the Tx to the d is actually bounded by d times d plus 1 to the d. Very well. Third main ingredient is Matsuzaka's main theorem. And today we would use a much improved version, which has been improved first, and for this business, maybe most importantly, by Kolla. But then I should definitely use the input of Demailly, Siu, Angern, Tsuji, and many others. They say that minus d plus 1, d plus 3 by 2 of the canonical class is very ample. Very ample means this gives me an embedding into projective space. This gives me an embedding into projective space, this bundle, but I know its Schoen class is bounded. And this is how boundedness comes about. So divisor star gives an embedding into projective space, but Schoen classes are bounded, and then I get boundedness follows from finiteness of Grothendieck's Hilbert schemes. So this is essentially the argument. And if you find this technical, then we haven't even discussed singularities so far. So how can this be made to fly in the singular case? And the answer is obviously it takes somebody like Birkar to do it. The first thing is this method of Mori finding many rational curves that hugely depends on deformation theory. And on these singular spaces, deformation theory just doesn't work. I mean, deformation theory is there, only it doesn't help. So this cannot be used. Instead, Birkar goes about in the first step of his proof and attacks this result directly. He's trying to find a bounded number such that this multiple of the canonical class will give you an embedding, or say at least a birational map. So he bypasses this major work that has been done here, attacks this problem directly with the use of Shokurov's theory of complements, about which I guess I can say next to nothing. The proof is a tour de force using inductive arguments of all sorts with the singularities, using asymptotic Riemann-Roch to produce singularities, and then induction by dimension by restricting to the singularities. But restricting to the singularities is really hard because you don't even know the singular set is normal and all sorts of problems arise. Or, working in a different direction, he's trying to argue by induction. So he's trying to argue inductively by setting up, like we have seen, a minimal model program that he will know ahead of time will terminate in a fiber space, and then he likes to look at the fibers and the base individually. However, you need to then understand the canonical classes of the fibers and the base, and this is hard. So there's a whole business called what is it called? Canonical bundle formula that does that, compare canonical class of fibers and base. And the problem is that this canonical bundle formula is notoriously ill-behaved under base change. In particular, base change when you resolve singularities. So he has to look not only at his space and the fibration and the pairs and the canonical bundle of those, but he defines generalized pairs, which is a bookkeeping device that takes track not only of the space and its vibration, but also of all birational models. And then, basically, you take main results from minimal model theory and you start again and prove everything in this setting of generalized pairs. So this is what makes this work extremely technical, but he manages to do this and proves directly a variant of this. Then you would like to use boundedness of volumes, boundedness of Schoen classes, but there's one catch. He does not know whether the classes that he produces are Cartier. They might be non-Cartier, and then things get very difficult, and this is the second of his main papers, dealing with those singularities, proving they are bounded by, in a very ingenious method, reducing everything to the toric case. But again, this is very technical and certainly beyond what I can do in minus 30 seconds. So thank you for your time.
des commentaires?
Okay, so you in step 1 you wanted to build a subgroup with a fixed point, and then because you said that in this case this is clear that there is an abelian subgroup, but the subgroup F is not abelian itself, I think.
Yeah. This is me trying to make the proof more simple than it actually is. The trouble is that that group F there is abelian itself, but this whole trick works only for automorphisms. You can't do it in the birational case. So instead of saying, okay, this is directly abelian, we have to argue and go the detour via fixed points.
Okay.
So I have a couple of questions. One is a small comment on the end. You write the sentence, get boundedness follows from finiteness of Hilbert schemes, but it seems that what you do is rather using the Chow variety, because you only mentioned bound on the degree. Well, at least what you have written is just C1 to the n, and then one can use the Chow variety. And how do you get, if you want to use the Hilbert scheme, how do you get boundedness for the Hilbert? Of course, we know both Chow varieties and Hilbert scheme, but is it the case that you can get in Hilbert polynomial directly from this, or?
I guess you can, but to be honest, I'm not overly particular with the details here.
Okay. Okay, and another question is, you mentioned the Borel fixed point theorem at some point.
Yeah.
It was not clear what you referred to. You had an abelian finite subgroup, and you had it acting linearly on a projective variety of some type.
That will have fixed points, yeah.
What?
That will have fixed points.
On any projective. Okay, this is the theorem.
Yeah. But then also on these spaces X that are equivariantly embedded there.
Not only on the full projective space, but also on the.
So it's not just that you find fixed points when your space is here, but you also find a fixed point on that space.
So this holds for any irreducible equivariant subvariety, or what? Oh,
yeah.
Okay.
Yeah, and Prokhorov-Shramov give full arguments for that. Yeah.
Other questions, other remarks? So if no, we can thank the speaker.